And yeah. So as you said, we're going to first give you a quick motivation, and then we're going to define what a quasi-category is, and in the end, we're going to show you what we can do with them by way of doing homotopy and as well as category theory. So first, let's start off with the motivation, and I'm going to start off with paths. So let's say you have got some topological space, and you've got a path in it. Then we define paths to be continuous functions from the unit interval or any interval into the space. And what we can do with paths is that if we have a path, pardon?
What is a continuous function?
A continuous function. So intuitively, a continuous function is a function that doesn't have any breaks. And if you do topology, there's a definition of a continuous function with respect to open sets. So maybe if you have done analysis, continuity is here as an analog of continuity of the epsilon delta definition. Is that is this a satisfying question? Or if you want continuous function, it means that, preimages of open subsets, which is some data you get from topological spaces, is that the preimage of open subsets is again open. Okay, so if you've got two paths, let's say you have one from A to B and one from B to C, then you can compose them. One way to do this is to just traverse alpha, for example, with twice the speed, and beta with twice the speed. And then you get a continuous function from the unit interval into X that sort of traverses both of them. And if you see this, if you draw it like this, you see, okay, well, we split the interval in half, and then we place in these paths and do everything from there. Now, the sad thing about composition is that it is not associative. So what I mean with this is that if you've got three paths, one from A to B, and one from B to C, and one from C to D, then there are multiple ways in which we can define one path to traverse all of them after each other. So, of course, one of them would be to first compose the first two on the left-hand side. Actually, I should use my stuff. So we could compose these two first, and then compose the result with the last function. And we would get something like this, where we traverse the first path alpha in 4 times the speed, and then beta at 4 times the speed, and gamma at half the speed. What we could also do is we could do it the other way around. So first we could compose beta and gamma, and only then compose the result with alpha. And we would get another function. So let's say we would write gamma.beta.alpha in this way. And we could see that these are not the same function. And that's a bit sad because, composition is, or if you have an operation, it would be very nice if we would make it associative. So there's one way to fix it, and that is to introduce homotopy. So if we say that two paths are the same if they're homotopic, we mean with this that if there is like a function from the unit square, such that on the top side or on the one side we have this one path, on the other side we have the other path, like this. So this gives us a definition of a homotopy. It is a continuous function from the unit square, such that on one end we get one path, and on the other end we get the other path. Is that all clear? Okay. So now this seems pretty nice, because now we've got associativity of paths up to homotopy, and also we've got inverses and other nice properties. So, for example, using homotopy and maybe it fits some more restrictions, we can define the fundamental groupoid. So maybe if you've done topology, you've heard about the fundamental group. The fundamental groupoid is sort of like that, but we don't impose a choice on the base point. So what it can do is sort of, if we have got a topological space like this disk here, and we cut out a hole in the middle, then the fundamental groupoid sort of detects that we've made a hole. And that's really nice because we can measure holes and we can define algebraic invariants of topological spaces. Yeah. Defining fundamental or defining what it means to be a groupoid is also not difficult, but it's also the way in which you want to do this is maybe can lead to more complicated or simpler definitions. The one that I like to give is that a groupoid is a category in which all morphisms are invertible. And if you don't know what a category is, then you would have to write it out all using, you've got a class of objects and composition and stuff. And that gets really tiresome, or rather, really, how do you say? You get a long list of definitions if you don't use the appropriate language to model groupoids. So as a quick summary, we saw that paths can be composed, but this composition is generally not associative unless we introduce homotopy of paths. And we could say, okay, we are done here. This is the end of the story. Everyone is happy because we got this nice result of the fundamental groupoid. But then we look at it a bit more closely, because by introducing the solution of homotopy, we introduce also another problem. So let's say you've got homotopies, two homotopies between three paths. Then we can compose homotopies. So if you think of homotopies as sort of as a function on this unit interval, then we can squish them together to get a homotopy from alpha to gamma in this case. I should use this thing. And we define it similarly to the composition of paths. Namely, we just traverse one with twice the speed and the other one after that. And sadly, this type of composition is also not associative. So if we've got three homotopies, then we can compose them either like this, by composing the top ones first and then with the second one, or we can compose the bottom ones first. And this is, again, not associative. So maybe you see where this is going. How do we fix this? Well, we could introduce homotopy of homotopies here like this. And, well, then this also introduces another problem, because homotopy of homotopies can also be composed in a very natural way, so analogous to how we did it before, but they're also not associative unless. So we would like to describe this type of structure using some formalism that gives us the ability to talk about points, paths, and homotopies and stuff. And this is where the idea of higher category theory comes from. So we would like to talk about things called objects and one morphisms and two morphisms and so on. And that satisfies some nice laws, such as associativity and composition and other things. So one might ask, okay, why don't we just do this? And the answer is that it's generally very difficult to have a nice formalism for this. So one thing we could do is we could start with objects and one morphisms and two morphisms and go up and up until some fixed n, and then stop there and say, okay, there are no things such as higher morphisms than n morphisms. And what we get is, for example, if we stop at n equals 0, so if we just as objects, we get sets. Okay, again, depending on your foundations, if you use sets in classes or small and large sets, you might have some issues with size issues, but for the sake of this talk, I'm just going to ignore them and just pretend that everything is a set. Or rather that the times where this isn't the case is not a problem, and we can deal with that at a later time. So, and if we introduce objects in one morphisms that compose associatively but not invertibly, we get ordinary categories. And if we also add invertibility, then we get the groupoids. Good. And what if we add some more stuff? If we talk about one morphisms and two morphisms, we get these things called bi-categories or general two categories, which there are multiple. So depending on your choice of your axioms, you get different definitions. And the thing about this is that the more and more morphisms you try to add up here, the more and more difficult it gets to define them rigorously in a nice manner. So for n equals 2, you get these tri-categories, or n equals 4, you get tetra-categories. Hello. Yeah. And to give you an idea of how insanely laborious this process gets, is to show you a small excerpt of a professor that wrote down the the axioms for a tetracategory using only the language of ordinary category theory, and we get these insane diagrams. And there are, I think I counted 46 pages of diagrams like this with all these, laws that you have to write down. And as you can see, you don't really want to go any further than that. Or maybe you want to, but maybe that's something that you have to choose yourself. So yeah. And there was another approach for doing infinity category theory, and that is to fix a model of which there are. So we choose some objects that we say, okay, this behaves the way we want, and we don't want to axiomatize these rules, so we just pick some model. There are multiple models. There are even more than what I wrote down. There are many, many more. But the quasi-categories are a model that are most extensively researched due to the works of André Joyal and Jacob Lurie, who wrote this a huge book called Higher Topos Theory, which sort of made quasi-categories stand out in and of itself. So one might ask, okay, why is it so hard? Did nobody manage to define them axiomatically? And then for this, I got a quote from Vladimir Hinich on his lectures from Infinity Category Notes. So he writes, the abundance of definitions of Infinity 1 category is somewhat similar to the abundance of programming languages or models of computation. All of them have in mind the same idea of computability, but realize this idea differently. Some programming languages are more convenient in specific applications than others, and the same holds for different definitions of infinity categories. So some people have shown that these models are in some sense equivalent. With that, I mean they introduce the same Quillen model structure, but writing it out is really difficult and not something I want to do in this talk. And yeah, this gives you an idea that there are multiple models, and we are just making a choice for quasi-categories because they're very convenient and easy to define, or they don't require a lot of knowledge in other subjects. So yeah, now we finally come to the definition side of things. So if you like definitions, this is for you. So we start off with simplicious sets. So this is because quasi-categories are special sorts of simplicious sets that satisfy some nice rules. And for this, we first want to define what a simplicious set is. So a simplicious set is, we can think of them as data that describes spaces built out of simplices. So here I've got some drawings of things you could call them simplicial complex or complexes, and the simplicious sets is sort of the abstract data that describes them. If you've seen the first talk from C. He defined them really nicely, and it was a very good introduction to them. So, as I said, quasi-categories are special kinds of them, so this is why we want to study these first. So, here's the first definition. A simplicial set is a functor from the simplex category into set. So it's a contravariant functor, denoted here. And the simplex category consists of the following data. So for all n in n, there is we have got these objects of finite ordered sets. So we can think of them as sets with n plus n1 elements, but with additional information that they are ordered in an increasing fashion. And we define the morphisms to be those that preserve the order. So writing this out a bit more, let's go through this example of this drawing of this shape that we want to describe using simplicial sets. So what it means is that for all n greater than 0, there's a set xn, which is called the set of n, which we call the set of n simplices. So if you know already what functors are, this gives you a definition of this, or rather we define this. But if you don't know about that, just ignore this comment over here. So here I wrote down the first couple simple xn's. So for x0, we first got the vertices, and in x1 we got all the lines that come from our simplex. But note also that we need to have these degenerate lines. So we will explain later why we need them, but also have those in mind. And x2 is going to consist of all these triangles, and plus the degeneracies that arise from the previous or the lower dimensional ones, and x3 is going to contain all the tetrahedrons, and so on. And yeah, so before we move on, I want to first talk a bit more about the morphisms. So what kind of special morphisms there are in this category. And there are two special types of morphisms in this category. So one is are the phase maps. So for every n, there exists exactly n+1 injective morphisms from this object to this object, and we can describe them simply by those that map every number to its target that omit one element in the target group. So for example, if n equals 1, then there are exactly two morphisms from this object to this object, which is omitting 1 or omitting 0. And we can interpret this as saying that we want for each line, we want it to have a rule that says, okay, for this line, this is the left side, this is the right side. So there are two kinds of maps from here to this side. And also note that we have this contravariance, because from here we go from 0 to 1, and here we go from the 1 simplex to the 0 simplex. And similarly, for n equals 2, we've got this triangle, and the phase map tells us that, okay, given this triangle, if we omit the 1, let's say, then we get this line consisting of the vertices 0 and 2 in this line over down here. There's another important class of morphisms in this category, which are called the degeneracy maps. So these are the surjective functions from n+1 to n. And so they are exactly the ones that repeat the number I. So for example, if we repeat the number 1, we get this triangle where two of the vertices are sort of on top of each other, and we don't really visually see this as being two-dimensional, even though it is. So the nice thing these simplicious sets is that they form a category. So let me go and zoom a bit more closely. So we define the category of simplicious sets to be the functor category of presheaves into set, which if we want to write it down or write it out, we get functors as objects or presheaves, and morphisms. These are the sort of the natural transformations, which is sort of the most obvious choice of morphisms if we have functors. So for those of you that are not sure what natural transformations are, so if we have got two simplicious sets, x and y, then a morphism between these simplicious sets consists of the data of these of rules that sort of transform n simplices of x into n simplices of y, such that for all morphisms in this simplex category, the following diagram commutes. So the nice thing about simplicious sets is that they are presheaves. So in fact, this category is a presheaf category, and in particular, it is also a topos. So we've got a lot of many of the things we can do with sets, we can do with simplicious sets. So we can define sort of projects, exponentials, and we can define subsets in particular. So before we move on, I will first give you some more examples of simplicious sets. So for every n greater than 0, there exists sort of the Hom functor. So we'll call this delta n, which maps these objects in our simplex category into the set of homomorphisms or morphisms from in the simplex category. So these correspond in some natural way into these standard simplices you might know from somewhere else. And there are also another important class that we will use in our definition of a quasi-category, which are the horns. So given like some fixed n and some k between 0 and n, there exists these horns, which we'll denote with these this horn shape, which intuitively there are the simplexes where we remove the interior of the simplex and also the kth phase. So if you want to write it out more clearly, they consist of the maps from M to N, so it's actually a subset of this, such that they factor through this jth phase map for j not equal to k. So here I've got some drawings. If we fix n equals 2, then this n to 1 horn is exactly sort of this shape, and or this 2 0 horn is exactly this shape, and so on, or the 3 0 horn is the maybe like a form of a cup if you want. Yeah, so we will use this as our definition for a quasi-category, but first we will give some more examples of simplicial sets. So if you've got a topological space, then we can define, oh, I've got a typo here. Then we can define a simplicial set in the following way. So maybe I should have said this before. So in order to define a simplicial set, it suffices to define the object or the sets, the set of n simplices, as well as the phase and the degeneracy maps. And the reason this holds true is that one can easily show that every morphism in this category, so every order-preserving map, factors through as a combination of these phase and degeneracy maps. So therefore, it suffices to define those, and the rest follows from this data that we give it. Is that clear? Okay. So here, in order to define a simplicial set, it suffices to define what these sets are. So, if you do it singular homology, we define sing xn to be the set of continuous functions from the standard n simplex into x. And then you have to define the phase maps, obviously. And the phase maps are created by sort of inserting the coordinate 0 at the ith position. And the degeneracy maps are created from taking neighboring values and adding them together, and sort of we get a shorter sequence or a shorter tuple. And this defines sort of a singular a simplicial set given the topological space. So what's nice about this functor or this association is that it admits a left adjoint called the geometric realization functor. So given some simplicial set, we can interpret this as a topological space in a very natural way. So defining it is, we define it usually using a colimit, but it's given if you have some easy, simple is the wrong word, if you have easy or nice simplicial sets, then the geometric realization is sort of the thing that you would expect. So for example, if you have this simplicial set delta n, then its geometric realization is going to be the standard n simplex, right? So, or if you have this simplicial set like right here, then its geometric realization is obviously going to be this thing interpreted as a topological space. Yeah. Great. So is it clear what adjoints are? Actually, I should have asked this before. Like, how many of you are familiar with functors? Okay. So with left adjoint, I'm not going to go into the details about adjoints, but maybe I can tell you why the word adjoint appears here. So maybe if you know from linear algebra, you can see if you've got a vector spaces V and W, and the function or linear map F, then its adjoint is going to be the function such that FVW is equal to V F adjoints W for all V and W. So sort of you can see some similarity between this condition and the fact that these are adjoint functors. Okay. then let's go over to the actual definition, the main thing that we've been always trying to do, and that's the definition of a quasi-category. So the quasi-category is nothing but a simplicial set that satisfies what's called the weak con condition, and we're going to explain the word weak later, which says that for every inner horn, so if we choose our k to be between 0 and n, then we can, for every function from here, or for every morphism from here to here, there exists some lift of this function from the n simplex. So here, this inclusion can be understood both, visually as a geometric interpretation, but also as I've said, because it is a appreciative category, there's a natural way of talking about inclusions. Or rather, actually, we can just go up here into the definition. We saw that, these maps, or the horns, are precisely maps from m to n that factor through it. So we can, simply use it as an inclusion of morphisms. Great. Oops. So there's maybe give you a bit about the history. So these quasi-categories were first defined by Boardman and Vogt in the 1970s, the early 1970s, and it was only later that we sort of saw that, hey, actually these quasi-categories are really nice, and we want to use them for infinity category theory. So they're also called weak concomplexes, and we will talk about concomplexes without the word weak. Also infinity categories, because again, there are the models, there are a nice model of infinity categories, so that's where these names come from. So examples of it are for topological space X, the thing that we saw earlier, Sing X, is a quasi-category. So maybe I should show it again. So the Sing X is sort of the place of continuous maps from the standard simplices into X with these phase and degeneracy maps. And in fact, it's actually more than a quasi-category. It's actually a concomplex, because first note that all horns, they are deformation retracts of these simplices, because you can just sort of easily fill in the interior, and because you are actually missing a face, you can do that. If you were not missing a face, so maybe you were have something like this, then this would not be a deformation retract anymore. But because we are missing one face, this is possible. So therefore, it follows that every horn is a filler, even those outer horns. So this gives us also another definition. A concomplex is a simplicial set such that every horn is a filler. That's a nice example. And there's also another example of quasi-categories, and they arise from a slightly different context. So given a category, we can associate to it a simplicial set. Maybe one way to justify this is, categories and simplicial sets, they may look entirely completely different, but actually, if we draw a category like this, we've got some objects like this, and morphisms between them, then it's sort of very easy to view it as a simplicial set, right? And we can actually formalize this to make it more clear. So again, it suffices to define the set of n simplices, the phase, and the degeneracy maps. So let's see, be a category. We define the 0 simplices of the nerve to be just the objects. We define the 1 simplices to be the morphisms. And the 2 simplices are pairs of composable functions. So if we've got these chains of functions, and for each n, we just take longer and longer chains. And then we have to define the phase maps, and they're just composition of at the ith object. So phase maps, actually, we want to, given some n simplex, we want to create an n-1 simplex, and sort of we can shorten it by composing these chains of functions at a particular index. So here you can see that we just composed these functions into one, and therefore we got a shorter chain. Then the degeneracy maps, like if you have a chain of maps, there is also a very natural way to make it longer, and that is just to insert the identity morphism. So we repeat the ith object, and just insert the identity morphism to get like a longer chain. And yeah, these nerves are also examples of quasi-categories. In fact, they are even something more than quasi-categories. They satisfy an even stronger condition, and that is that every inner horn has a unique filler. So here we've got, there must be a unique filler in this sense, and it follows from the fact that in an ordinary category, composition is unique, right? So another way to view this is that if you've got this two-cell, the two-cell consisting of this data sort of witnesses the fact that if you have got two morphisms like this, I call F and G, then there exists a two-cell, and this two-cell represents their composition G composed F. And because in ordinary categories this is unique, this gives you this unique extra condition. So as a quick recap, so we can watch over. Well, actually, there's a nice theorem about these nerves. In fact, that is the following proposition: a simplice set satisfies sort of this unique inner filler property. So this thing I wrote up here, if and only if it is the nerve of some category. So this gives you another way to view these nerves, or we could use one to define the other, vice versa, which is pretty nice. So here I want to give you a quick overview. So we defined quasi-categories and concomplex and nerves, and sort of the defining feature of the quasi-categories is sort of their generalizations of both concomplex and nerves. So every concomplex is a quasi-category, and every nerve is a quasi-category, but in this section we don't really have an implication. So here I wrote it down. So we've got this inner horn condition here, and also these non-uniqueness from the concomplexes. Questions until here? Okay, so I'm going to move on. So now we can go into the nice things about quasi-categories, what makes them so interesting. And the thing is that we can use them to do both homotopy theory and category theory. So first, let's talk about the homotopy. So if you are given parallel morphisms, then we can say that they're homotopic if there exists some two simplex such that one of these things are just, so if there exists duplices of this form, of this shape. So note that these here we've got the degeneracy maps, right, which sort of gives you, given a single object B, it gives us this morphism from B to itself. And then we can sort of interpret the two simplices as homotopies of one simplices, and three simplices we can interpret them as homotopies of two simplices, and so on and so forth. So that's pretty nice. And there's also sort of as a sanity check, you know, if we call it homotopy, then it should behave like homotopy. And there's this nice proposition said that the homotopy defines an equivalence relation on morphisms, and this follows precisely from the weak con condition. And I'm not going to really go into the details about this. So this was the homotopy side of things, and which is so we can do homotopy with quasi-categories, but also we can do category theory. So if you're given some quasi-category, then we can view it as a category in a certain sense that we define objects to be its one cells, objects to be its zero cells, its morphisms to be one cells, and composition is then witnessed by two cells. So I'm just going to move on and explain what I mean with this witness thing a bit later. And the last point is that we have, in an ordinary category, we also need identity morphisms, and they also arise from these degenerate one cells. So that's where we get all this data from. So let's talk about why they are not strictly seen as categories in this fashion. It's because composition is not generally unique. So if you remember this weak con condition, it says that given this horn, there must exist some filler, but not a unique filler. So and the way we can sort of finish this analogy is that, or to finish this perspective from the categorical side, is that they might not be unique, but they are unique up to homotopy in the following sense, is that we can, for every pair of composable morphisms, there exists a simplex that called comp-FG, which consists of sort of candidates for compositions of these morphisms. So if you remember, if you go back to the very beginning, right, we had these paths, and we saw that composition was not generally unique. There were multiple ways to parameterize these paths, so we get different paths. But all since they're all homotopic to each other, and that was sort of the thing that we are seeing finally now. So let's go back down. Oh yeah. So there's this proposition that says that this the space of compositions is contractible. So generally, we've got this nice analogy that in an ordinary category theory, in ordinary categories, uniqueness is replaced with contractibility of spaces. So that gives us this nice interplay between homotopy theory and category theory. Yeah. So the last point, maybe you were wondering if you really like, if you think this is nice, but still were wondering, okay, why is there no axiomatization of this? Or in fact, there are some axiomatization of this. There are actually multiple ways to do this, and I'm going to show you, or going to just tell you about one specific way to do this, and that is done by a joint project by Emily Riel and Dominic Verity. They released this great book, Elements of Infinity Category Theory, and how I'm going to say this. So they what they did is they defined the axiomatization of infinity categories in a larger structure called infinity cosmoi. So maybe if you've heard about topos before, a topos is some context in which you can do set theory, right? And a cosmos is some setting in which you can do category theory. So an infinity cosmos is a setting in which we can do infinity category theory. So that seems really promising. And what they showed is that given some different models of infinity categories, so complete Siegel spaces and Siegel categories, they define like these adjunctions between these categories, or between these categories of complete Siegel spaces and Siegel categories that show you that they are equivalent, or that give you the structure in which they are equivalent. So if you want to learn more about what exactly this means, that they are equivalent, is that they give rise to the same model category structure. And if you want to read more about this, you should just talk about, learn about Quillen equivalences, and that's a really nice topic. So yeah, I've reached the end of my talk. If you have any other questions about this topic, just feel free to ask me after this in the apero. And yeah, thank you for listening to me.